Hey Algebros! Before we get into lesson, let me just say I am brimming with excitement to get started with this unit. You've probably heard me talk about this in the classroom, or outside the classroom, that's just how much I like it, but I love this unit in Algebra 1. It is my absolute favorite because it takes everything we've been doing so far and turns it into something absolutely beautiful. And I hope you guys grow to enjoy it as well. But before we get started, we need to look back a little bit to linear equations and talk a little bit more about what can happen in some special cases. We've already talked a lot about linear equations, solving them, what linear stuff is all about, but let's go into a little bit more detail when we have two linear equations that come into collision. We've already roughly seen this with our sample problem. So, we've seen a case of colliding equations in our story problem. And that's usually a case when you have two linear equations. Let's say one is f. I'm just calling it a name here. Another one is g. And let's say f was y equals, I don't know, let's bring Dotson back. And this time Dotson has a sideways cap. And G is Dotson's buddy, Dotley. This one has, I don't know, red hair and a ponytail. But it's not just Dotley. It's Dotley plus a fish. What we would do in those cases is we want to find where do they collide. And we can find this. Oops, didn't mean to do that. We can find this by setting the y's equal. Can't write today. That's a whoopsie. Setting the y's equal. So in this case, the 1y for f equals the y for g. And what that means is Dotson and his sideways cap equals Dotley plus the fish. That's not a fish, that's an infinity sign. That's a fish. And don't forget Dotley's hair and ponytail. And yes, you need to write these as well, all the way down to the ponytail. So now imagine this, but instead of dot figures and fish, now you imagine it with numbers. So taking a numerical example now, let's say one of the equations was 2x minus 1, and the other one was 3x plus 1. So this came from two equations. One of them was y equals 2x minus 1, which would have been a straight line on a graph, and the other was y equals 3x plus 1. Both of these would have been straight lines on the graph. And then we solve this as we normally would, and we already know how to solve linear equations. Start by moving all the constants to one side. I'm doing that by removing the minus 1 from the left. So I'll be left with 2x equals 3x plus 2. Then I'm going to move all the variables to the left. By that I'm subtracting 3x from both sides. I'm left with negative x equals 2. Then I need to reverse signs, so I'm going to multiply both sides by negative 1. So far, I haven't done anything brand new. If there's anything that you feel a little bit lost about, I'll leave a link to the playlist for linear equations and solving linear equations in the description of this video. But so far, we've done this all algebraically. What does this look like on a graph? Well, on a graph, what this amounts to is as follows. It's going to be 2 intersecting lines. And we can show this in detail too. Let's boot up graphing software, either GeoGebra or Desmos, whichever one I see here on my iPad. Hope you're enjoying the glorious view of everything that I have right here, and I'm getting lost. Let's use GeoGebra. Tend to like that one a little bit more. We're not going to use graphing software all that intensively here. I might ask you to use it to make things simpler for the sake of a you-try question, but we're not going to go too wild with it. I'm going to ask you guys to do the graphing on your own. And again, it's something we already know how to do. So let's give ourselves two equations. The first one is y equals 2x minus 1 to x minus 1. As you can see, it automatically plots it exactly as it should be. And the other one is going to be y equals 3x plus 1. 3x plus 1. So as you can see, this amounts to two straight lines that intersect at one point. That point is right over here. The intersection point is -2, comma, -5. And look at that. That -2 that we just saw when we solved it algebraically, right here, that matches up perfectly with this one right here. Matches up absolutely perfectly with the x-coordinate of our intersection point. So one thing to keep in mind, this is the x-coordinate of the intersection. So I'm going to supply you guys with graph paper, and with that graph paper, I want you guys to roughly sketch this. All right? You'll have enough space on it in order to draw the two straight lines, and I want you to highlight that intersection point. Don't worry, won't take you too long. I'll let you pause the video right about now. So we've just talked about a very standard case when we have two intersecting lines, and the intersection point is what we call our solution. We'll talk more about solutions later. But for right now, there are other possibilities. There are two odd possibilities, which I might have mentioned already in class, or given as like a bonus green card question at this point. But now we're going to talk about them in more detail. The first one is the case of no solutions. For the case of no solutions, algebraically, that's when we get something that's just straight up impossible. This happens when we solve and get something impossible. So let's see that in action with another set of equations right here. Let's take an example, an egg, if you will, of 5x plus 3 equals 5x minus 10. Algebraically, if we're going to approach this, let's start by moving the constants to the right. Subtract 3 from both sides, and we'll be left with 5x equals 5x minus 13. Now, you might already start to see something doesn't look right here. But let's see what happens when I try to move the variable terms. And then the oddity will really show. Keep in mind, on this left side, 5x minus 5x is just 0. It's opposite terms and they cancel. And look what's left on the right-hand side. Negative 13. Oh no! 0 equals negative 13! The world is exploding! Anarchy has risen! Run! No, I'm kidding. No running. No, instead, what you can say is that this is impossible. So there is no. Let's be a little bit more specific right here. No real solutions. The reason I'm making that specification of no real solutions is because we do have things called imaginary numbers, and we might end up with stuff like that with some equations, but in this case, no. No real number solutions. So, graphically, this appears as two parallel lines. Note that before, the intersection point denoted a solution in our previous case. In here, if there is no real solution, that implies that there's no intersection. No intersection. So graphically, these two lines will never, ever cross paths. Let's see that in GeoGebra. Let me erase these two straight lines, and let me replace them with 5x minus 3, 5x plus 3 in this case, my bad, 5x plus 3, and the other one is 5x minus 10. Check this out. No matter how far you go with these two straight lines, they will never, ever, 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 ever cross paths. They will go on and on forever, side by side with each other, like two lanes of the highway. With no intersection, we get no solution. So once again, I will give you guys a minute or two on the second sheet of graph paper that you have taped into your notebooks, or drawn freehand, however we go about this, to pause the video and graph these two equations. All right. We have one more oddity left to have a look at. Don't know why this is not working. Hold up. Do I have to close the app? Yeah, let's close this and see what happens. Hold on a sec. Sorry, guys, technical difficulty. Okay, now it's working. All right. So now, we finished up odd case number 1. There's still one more odd case, which is when we have infinitely many solutions. Note that this does not mean that the solution is infinity. So I'm going to leave this as like a side note over here because it's a very common mistake and a common shorthand that is actually mathematically incorrect. It is not the same as saying the solution is infinity. Keep in mind that infinity isn't really a number, so to say. It's more so a concept to help us understand it. All right? To understand a really big number. So, algebraically, this is when you get, something that is always true. So same thing on both sides of the equal. Usually you want to end up with like a 0 over 0 just to be safe, but we can identify same things on both sides sooner if we so choose. Let's take an example right here so we see what we're talking about. So in this case, let's say we have 3x plus 15 equals 3 into x plus 5. Well, let's start off with the distributive property on the right side. We'll get that 3x plus 15 equals 3x plus 15. Here, we already kind of noticed something really peculiar. 3x plus 15 over here, 3x plus 15 over here. That kind of already satisfies our condition. This already satisfies our condition. But let's go further. In case you don't recognize this or spot it immediately, you will spot it eventually. Let's subtract 15 from both sides. You'll end up with 3x equals 3x. Once again, same thing on both sides. If we were to subtract 3x from both sides, we'll end up with 0 equals 0. So, since this is always true, so any x value makes this work. Alternatively, over here, with no real solutions, you can add this note: no x value works. Try as you will. None of these x values will work. And again, 0 doesn't equal negative 13. And I'd love to see anyone who tries to die on the hill that it does. All right? So, this in mind, you may wonder what this looks like graphically. Back to our main objective here. Graphically, this means the two linear equations do something that we call coinciding. The two linear equations coincide or they're basically the same line, or they're the same line. Note what this ends up looking like. So if we had one straight line looking something like this, and another one, that's basically the same thing on top of it. It's literally the same line. Literally the same as the red. That means that basically every single point is an intersection point. So every point is an intersection point. Let's see this in GeoGebra. Once again, let's erase these and let's go through our paces. Y equals 3x, almost did the times sign right there, plus 15. And the other one was 3. Oops, nope, 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 nope. Stop doing that, stop doing that. Bad, bad. Would be 3, open parentheses, x plus 5. Oh, look, I only see one straight line. And that's because this straight line is the same in both cases. That being said, there's only one possible solution. Sorry, no, there's infinitely many solutions. My brain just turned off right there. There's only one straight line, infinitely many solutions. And now I'll give you guys a second to pause the video and sketch these out. All right, and we are back. So now, as a bit of a recap, or I guess takeaways, there are 3 possibilities for the solutions to a linear equation. One solution, x equals a number, and we have intersection point. One intersection point, let's be specific here. No solutions, we get something impossible. Something impossible. Typically 0 equals a number that's definitely not 0. And here we have no intersection, parallel lines. And finally, for infinitely many solutions, that's a case where we have something that's always true. And we have 2 lines coinciding. Coinciding or overlapping. All right. For the U-try today, I'm not going to ask you to do anything graphically. I'm just going to ask you to solve algebraically. So for the U-try, solve each equation for x. The 3 equations I'm going to give you, 3x plus 4 equals 3 into x minus 1 plus x. The next one is 3x plus 4 equals 3 into x minus 1 minus 10. And the last one is 3x plus 4 equals 3 into x minus 1 plus 7. Right? Solve those for next time. We'll solve them together as a group, and we'll even look at them graphically as well, just as an extra visual aid. I'll see you there, and I can't wait for the rest of this unit. Man, am I excited.